Okay, so it says a student determines the density of an unknown metal with a mass of 32.56 grams. The student partially fills the graduated cylinder with water and measures the volume of water to be by itself 14.78 grams. The student then allows the metal, to water. The student then adds the metal to water and measures the new volume as 20.44 milliliters. What is the identity of the metal? Okay, so let's try it out. Graduated cylinder is basically a device that we use for measurement, particularly volume, right? So they tell us that they take a piece of metal and they drop it in the graduated cylinder, right? At first, the graduated cylinder with just water is at 14.78 milliliters. Then they added the piece of metal. So here's the water right now. They added a piece of metal. Okay, so then it goes up to 20.44 milliliters. So what would be the volume of the metal?
Would you just subtract the 20.44 from the 1478 or 1478 from the 2044?
Yep, that's exactly what you're going to do. So we got 20.4 milliliters minus 14.78 milliliters. And then that's going to give me my volume of the metal. Okay, so let's go do that. Okay, so then I get 5.66 milliliters. Okay, so that would be the density of the metal. Okay, and we know that, not the density of the metal, that would be the volume of the metal. Okay. So to calculate the density, what is the definition of density? Maria? Anyone?
here, but I'm just trying to find like the definition of it.
Okay. The first thing that I would always do is I would look at the notes, probably of the chapter that we just talked about. So if I go to my syllabus, I mean, if I go to, I'm sorry, the Canvas shell, I go to modules. I'd go to chapter 3. Let's see. So you see chapters 3, measurements. Oh, that's the recorded lecture. Let's see. I go to unit 1. Chapter 3.
It.
So yeah, this is my PowerPoint presentation.
Yeah, I already have I have those like on hand with me.
Okay.
So I guess density is the mass per unit volume of a substance.
Okay, so it's mass per unit volume. Okay, so then if we go here, mass per volume. Okay. Now, do we have all those components? Do we have mass and do we have volume? So we just calculated volume. Do we have the mass?
Yes.
Okay, so then I can actually plug it into the equation, right? To calculate my density. So then I have 32.56 grams divided by my volume, which is 5.66. How many sig figs should I have?
Don't you have 3 sig figs? Because the first
That's right,
one
3 sig figs. So my answer is going to be 5.75. That's grams per milliliter. Okay. Thank you, Vernice. Sorry, I just opened my chat window. Okay, pretty simple, not too hard. So the key to any problem, first off, you got to figure out what it is that you need to find, what we're looking for, right? And then what tools are available for us, right? So the first thing that I would always do, I would always have my notes, especially when you're doing your homework, right? Until you start getting comfortable with it. Once you start getting comfortable with it, it'll start sticking, right? The more you do it, the more comfortable you'll get. It'll start sticking up here, and then you won't need your notes, right? But in the beginning, have your notes available, go through your notes, okay, density, what is density, right? Okay, and so I would print out, I have a binder with all my notes from when I was in college. I still have that binder, in storage mostly because a lot of it's up here now. But when I can't remember something, I go into storage and then I'll find that binder to sit there and look at it. Or I'll find a book that tells me about it. Or I'll go to one of the links that are on the Canvas shells. With that particular topic. Okay. You guys want to do one more? Or are you guys good?
Sure, let's do one more.
Okay. clear my screen.
I was also curious, will our tests have problems like this one, like similar?
Yes. Oops. Very similar to that one. Yeah. And only thing, it'll be more open-ended. You won't have multiple choice. So you'd have to figure it out, you know. Sorry, I screwed up and closed my Chem 101. Okay, what problem do you guys want to do? Is there one that you're itching to get done? $44, okay. Okay, it says you're renting a car which is reported to achieve 10.1 kilometers per liter. How many miles will you be able to drive on 11.0 gallons of gas? Okay, so let's see what we know or what we can figure out. So we have gallons of gas, and then we have this conversion factor, which changes kilometers to liters. So aren't gallons volume? Is that true? Gallons are volume. Okay, that's right, gallons are volume. And aren't liters volume? Okay, so we know that liter is also volume, right? So we need to sit there and convert our gallons to liters before we can use this conversion. And then we also have to convert kilometers into miles. Okay, so I know that there's a conversion factor in my notes that has gallons. To liters. So 1 gallon, if I remember correctly, I think it's chapter number 3. So I'm going to go through my chapter number 3 notes, or I'm going to go to my table, my packet that I printed out, that Dr. Henry told me to print out and make sure that I have available with the periodic table. Let's see.
On my homework, it says 11.5 kilometers per liter. It doesn't say 10.1.
You said, what was that?
On my homework, it says 11.5 kilometers per liter instead of 10.1.
Yeah, it's going to change. It's changing per homework assignment. Every homework assignment is going to be slightly different. The concept is the same, though.
Okay,
right?
just making sure.
It helps keep you guys honest, you know. You guys are working in groups. Did you guys see these packets that the chemistry says chemistry packet or chemical
Yes.
packet, right? You guys
Mhm.
printed it out?
Yes.
Okay, so if you go through there, there's a conversion table. It's on the second page. It looks like this. So if we look at it, we want to change liters to gallons. Okay, so if I go and I have 1 gallon, if I look at the very bottom, let me see if I can pull up the packet on your screen. Okay, can you guys see it on your screen?
Yes,
The
we can
very
see it.
table. Okay, so let's make it smaller so we can actually use it. Okay, so if I have 1 gallon, come down here to the bottom of the table here. Let's see, 1 gallon, that's going to equal 3.785 liters. So 1 gallon is going to equal 3.785 liters. And we know that kilometers, so 1 mile is going to equal 1.69 kilometers. Okay. So my given is going to be 11.0 gallons. So we're going to start off with that. So I have 11.0 gallons. Okay. So if I want to get rid of gallons, how am I going to do that using this conversion factor? And I want to end up with liters.
Multiply by 3.785 and then divide by a gallon.
Okay. So I'm going to multiply by the 3.785 liters. And I'm going to divide it by 1 gallon. Okay. So then that allows the gallons to cancel out. Okay, so now I have it in liters. My units are going to be in liters. So then I can use this conversion here, right? To get rid of my liters and to get kilometers. So how would I use that? Who's going to be on top? Who's going to be on bottom? So I can use this conversion up here, that 10.1 or whatever your value is. So-
Kilometers go on top, and then the miles on the bottom.
Okay, so if I heard you correctly, I'm going to put my 10.1 on top, and that's going to be kilometers. And then I'm going to put my liters on the bottom, so it's 1 liter at the bottom. Okay, so then in this case, the liters are going to cancel out. Okay, so now I have my units are going to be in kilometers. And so how do I get from kilometers to miles? Anyone? Anyone there?
Put the 1.609 kilometers on the bottom and 1 mile on
Okay.
top.
So I'm going to put 1.609 kilometers on the bottom and 1 mile on top. Okay, so then it's going to cancel out. Okay, that's going to equal, we do the math. So how many sig figs should I have?
Three.
Well, in this case, these two are conversion factors, so we're not going to use these guys. So here we have 3, and here we have 3. So my answer should probably be
3.
3, right? Because we take the lowest number. And since they're both 3, okay, so I should end up with 261 miles, 261 miles. So let's see if that works out. Okay, 261 miles.
How do you get that answer? Like, what do you like multiply?
The top part is multiplied. So we multiply 11 times 3.785 times 10.1, and then we divide it by the numbers on the bottom. So then we only have 1 and 1, and then we have 1.60. 1 and 1 multiplied by anything is going to be itself. So then I just divide this by 1.609. And so then that's going to give me my 261.
Okay.
Okay. So again, if it's on top, we multiply it across. If it's on the bottom, that's going to be division. Okay. And again, if you take a look at your notes, when we do those sample problems, I try to sit there and go through that process of how I go about it with crossing out the units. Pay attention to that. And you can apply that to pretty much anything. And think about what you're starting off with and what you want to end up with. Okay. At the end of the day, the units that we want to end up with should be on top. Okay. Here we wanted to end up with miles, and we have miles on top. Okay, so let me clear this. Okay, so let's see. Let's go ahead and get started with the chapter 5 lecture notes. So we're doing chapter 5 right now. Okay. So there's this scientist named Dalton. Dalton was actually a teacher and a school teacher, and he came up with these theories. And so Dalton basically has what he calls his atomic theory, talking about the atoms. And so he came up with these few theories, and I want you guys to sit there and think about them as we talk about the various components of an atom. And then I want you to figure out how many of these theories are actually true today, knowing what we know, okay? So the first theory was each atom is made up of individual particles called atoms. The second one was atoms are indivisible. Then he said that atoms of one element are identical in every respect. And then he says atoms of one element are different from atoms of another element. And then he said that atoms of one element combined with atoms of another element can form a chemical compound that has small ratios that would be exactly the same. Okay, so his first one was atoms of an element elements are made up of atoms. All atoms of a given element are identical. So he basically said that they look exactly alike. Okay, so, and then he said that atoms are indivisible, which is the same thing as saying that an atom cannot be destroyed or created. And then he said all atoms of a given element have the same properties, including mass. So they're exactly identical. That's exactly what he said about a given element. So one carbon atom is going to look exactly like the other carbon. Mass and everything. Okay. And then he says atoms of different elements have different masses. So for instance, we have carbon and nitrogen. Well, carbon weighs 12 on a periodic table, and nitrogen weighs 14. So they have different masses because they're different atoms. Okay. And then the last thing he said was that atoms of a different element may be combined in small ratios of whole numbers to form compounds. So let's start out with that last one. So the law of multiple proportions basically says that when we combine two or more elements, those elements can make a compound. And then that compound is going to be based upon the ratio of each of those elements. So for instance, we have carbon monoxide. Carbon monoxide has one carbon and one oxygen, where carbon dioxide has one carbon and two oxygens. These guys are two different compounds. They're going to behave differently, but they're made up of the same type of atoms, right? So these guys are going to be able to be put together in simple whole number ratios. 1:1, this guy, 1:2. Okay. And then if we combine this ratio, combine these two together, they're going to have a different weight compared to these guys that are 1:2 ratios. Does that make sense? Okay. Acknowledgement. Remember acknowledgement. Thumbs up, crying if you don't get it, some way of telling me know that you guys are there and that you guys understand what I'm talking about. Or just a simple yes, got it. Okay. So let's get to the nitty gritty. So if we think about an atom is composed of three parts. We have what we call the electron. The electron is a negatively charged particle. This is a subatomic particle. Subatomic basically means below or smaller than the atom. So the electron, it basically has a mass of 1 divided by 1,837, the mass of a hydrogen nucleus, which is just a proton, okay? So it is 1 divided by 1,837, the mass of a proton. So in other words, the electron is kind of like if I had a speck of dust on my shoulder, right? And I weighed myself, is that dust going to have an impact on my weight? In all honesty.
No.
No, it isn't, right? I'm going to pretty much I weigh 220. I'm going to continue to weigh 220, right? Because it's so small that it's not going to have a real impact on the weight. So that's exactly what the electron. The electron is so small that it doesn't affect the weight of the atom. Okay. So we have electrons. We're going to use the symbol E minus, standing for electrons. Okay. We know electrons are going to be negatively charged, so they're going to have a -1 charge associated with it. Each electron has a -1 charge associated with it. Okay. A proton, which we're going to use P plus, a proton has a positive charge associated with it. And then we have what we call a neutron. So we're going to use NO. A neutron is neutrally charged. So it has a 0 charge associated with it. Okay. So neutron, neutral, 0 charge. Proton, positive. P for positive. Electron is going to be negative. Okay, you guys got that? Okay, so now we're going to stray from our notes a little bit. You can use the notes. We'll come back to them here in a minute. Okay, so we're going to go to the periodic table. Maybe it lets me. Okay, so we have the periodic table here. So let me pull this up. Move this around. Oops. Okay, so if we take a look, we'll start off with hydrogen since we've already talked a little bit about hydrogen. Okay, so this number here at the very top, I'm going to circle it in red. This number here is called the atomic number. Okay, so the atomic number defines the element or the atom. Okay, it also tells us the number of protons. The atom has. Okay, so hydrogen has how many protons? Bernice? That's right. Hydrogen has 1 proton because the atomic number is 1. Okay, so let's look at another element or another atom. Let's look at silicon. Silicon has how many protons? 14, that is correct. Okay, so that tells me how many protons I have. Now, the thing about atoms on the periodic table, atoms themselves or elements are going to be neutrally charged. Neutrally charged meaning that they're going to have a total 0 charge associated with it. Okay, so if I have 14 protons and protons are positive, how many electrons must I have? Anyone? So in the case of silicon, silicon has 14 protons. How many electrons must I have to balance it out? So it has a total charge of 0.
Is it 14?
That's right. So I need to have 14 electrons. So we know that silicon has 14 protons and 14 electrons. Okay. Let's see if I can put that somewhere else. Okay. So okay, this here is called the atomic mass. So this is the mass of the atom. And often we can also call the atomic weight. So the atomic mass is going to be made up of the mass of the protons plus, or the number of protons plus the number of neutrons. Now, if we look at this value here, this is a decimal value, right? 0.085. So if I cut you in little pieces, are you gonna be okay?
No.
No, you're not gonna be okay, right? So we want to try to put it as a whole number. So what we want to do is round this number up or leave it alone, the 28 to leave it alone. So it'll be a whole number. And this number is going to represent what we call our mass number. Okay, so this guy is 28.0. So if we take a look at this 0 here, are we going to round it up or are we going to just round it, leave it at 28?
Sure, we'll just leave it at 28.
Okay, so 28 is going to represent our mass number. And again, it's just we get our mass number by rounding our atomic mass. Okay. Running out of places to stick stuff. Okay, so we have a mass number of 28. So our mass number is going to equal number of protons plus the number of neutrons. So if I have my mass number, I can calculate the number of neutrons, right? By just subtracting the number of protons by that mass number, or subtracting the the mass number by the number of protons. Okay, so in this case, we have 28 minus, how many protons does silicon have?
14.
14. So that means that we have 14 neutrons. Okay, you guys see that? So silicon has 14 protons, 14 electrons, and 14 neutrons. Okay. So what I'm going to do is I'm going to circle a couple of elements. And what I want you guys to do is to tell me how many protons, neutrons, and electrons that you guys have. And there's only 6 of you guys, so I'm not going to put you in a room to do it. You guys can do it here. Talk among yourselves or type among yourselves. So the first one that we're going to do is going to be cobalt. The second one that we're going to do is potassium. And the last one that we're going to do is cesium. Okay? So I'll let you guys do that right now. Okay? So let's go ahead and get started. I'm going to go ahead and clear off my screen, or at least the text part of it. Okay, so let's start with potassium. I saw that you guys so potassium, somebody said 19 protons. How many electrons? 19 electrons. And then how many neutrons?
20.
20. Okay, where do we get 20 from?
So like from the mass, you subtract it from like the number of protons you would already have.
That's right.
So the mass didn't change. So it stayed at 39 because it couldn't be rounded up.
Okay. So 39 minus 20, 39 minus 19 gives me 20, right? Yep. Good job. Okay, so that was for potassium. Okay, so let's do cesium. Okay, cesium. Okay, how many protons?
55.
Okay, so we have 55 protons. How many electrons?
55.
And then how many neutrons?
78.
Okay, and how do we get 78?
Because you round up the number for the mass to 133.
Okay, so 133 minus 55 is going to give us 78. Okay, and cobalt. Okay, how many protons for cobalt?
27.
Oops. How many protons for cobalt?
27.
27. How many electrons for cobalt?
27.
And how many neutrons for cobalt?
32.
Okay. Piece of cake.
Yeah.
Everyone else is good? Okay, good. Okay, so let's go back to the lecture. Okay, so let me give you a little bit of history. So the electron was basically, the discovery of the electron was basically given to J.J. Thomson. Okay, so J.J. basically had theorized that the electron was kind of like in a, have you guys ever had bread pudding? No.
No.
So bread pudding is basically you take stale bread, you add some sugar, you add cinnamon, you add milk, you mix it all together, and it's this hot mess of type of thing. Some people put caramel and stuff in it too, right? And so it looks like a total hot mess. And so things are like randomly everywhere, right? And so J.J. Thomson basically theorized that the electron is kind of like that. He is like, it's this in this gel matrix, and there's all randomly all over the place, and so there's no order associated with it. Well, and so his theory was it was like plum pudding. Plum pudding is kind of like bread pudding, okay, where it's just a hot mess and everything was everywhere. So you had charges everywhere. Your pluses and your minuses are everywhere. Okay. So Rutherford, another scientist, basically said, I don't know about this, right? So what he had done, he basically took alpha particles. Alpha particles are positively charged, okay? And he took a thin layer of gold foil. And then what he did, he took this, let me get my pointer here. He took his alpha particle beam and shot it at the gold foil. And then, so what he saw was that you had things that weren't deflected, and then you had things that were deflected. So if we have two positive things coming together, what happens? If we have two positive charges coming together, what happens? You guys ever play with a magnet? Two positive ends. They don't attract, right? They actually repel. So if we have two positive things coming together, they repel each other, right? And that leads to a deflection. And so what he saw was that by putting these positive particles and shooting them at the gold foil, there were areas that would deflect the beam, which means that your positive charge was centralized, right? And then if it was able to sit there and attract, it would actually go through because the beam is going fast enough. It'll just slow down the beam, being that negative charge, but it would be able to go through, and it kind of helps it manage its way through. And so you had things that were able to go through and things that were diffracting, right, or deflecting. So because you had things that were deflecting and things that were able to go through, it kind of gave us organization because it was very organized in the way it was done, right? And that suggested that we had what we call a nucleus. So our positive charges are located in the nucleus. the electrons are located in this, what we call an electron cloud on the outside. And this electron cloud is like a spacious area where the electrons are constantly moving, okay? So in the center, we have, in the nucleus, we have our positive charge, we have our proton, and we also have our neutron. Okay, so Rutherford I kind of looked at this, and with the help of another scientist, a Japanese scientist, and I can't remember his name at the time, who came along the same kind of concept around the same time, he discovered that, hey, there's a nucleus. And that although an atom is mostly empty space, and that empty space is going to be occupied by the electrons moving, right? We have that positive, dense center charge. So it looks something like this. So this is what the nuclear atom is shown to look like, where we have the nucleus in the center. Nucleus in the center, and then it's covered by this electron cloud. Okay, and so our nucleus is composed of our protons and our neutrons, which is also where all of the mass is coming from. Okay, so if we take a look, the nucleus is going to be 10,000 times smaller than the atom itself. So the atom is going to be huge compared to what the nucleus is, even though the electrons there that are making up that cloud area are really, really tiny. Okay, so in other words, those electrons are really moving, right? And they're moving in layers, like in an orbit. Okay. So, take-home message: most alpha particles weren't deflected, but there were a fraction that were, and that's that deflection was sort of uniform when it repelled, and so it was really organized in that area. So that meant that a large part of it was open space. Only a small portion of it, a small fraction of it, would deflect. Okay, so that means that the atom itself is going to be composed primarily of open space, and then that positive charge is going to be really tiny, but it is all positive and it's all centralized. Okay. So Rutherford, at the same time, helped us understand how the atom was organized, also showed that there were positive charges in the nucleus, right? And so you guys already know what a proton is. It's positively charged. And now you know what a neutron is. And a neutron was credited to James Chadwick. We won't talk about how he figured that out. We already talked about the electron. Okay, so now let's talk about isotopes. Iso means same. So if you see that prefix iso, it means same. Something is going to be the same. An isotope is atoms that are the same element, but they have two different masses. Okay, now I've kind of discussed this already, and I want you to get guys to think about it a little bit. So if we have isotopes that exist naturally in nature, right? So basically they're elements that are they're the same element, but they have different masses. Now, what defines the element? What makes carbon carbon? Anyone? Just mentioned a few minutes ago. Okay, so for a reminder, what makes carbon carbon is the number of protons it has. The protons are never going to change. The protons are always going to be the same. So carbon has how many protons?
Six.
That's right. Carbon has 6 protons. So carbon will always have 6 protons, okay? But carbon has what we call an isotope. There's carbon 12, which is what we have on the periodic table, essentially. We also have what we call carbon 13. And then there is also carbon 14, but it's very, 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 very little of it. Now, these 3 isotopes all exist in nature, meaning that they all occur, but they occur at different percentages. The majority of it, we're going to say about 99.9% of it, it's going to be carbon 12. But you're going to have some carbon 13 and some carbon 14. These guys are going to be pretty low compared to this guy. And if we take a look at that mass, the actual mass of carbon is like 12.011, right? Carbon 12 weighs 12. Carbon 13 weighs 13. So if we do the calculation, we can calculate how much carbon 13 we have based upon this value. So this is going to represent that little bit of carbon 13 that we have. And carbon 13 is more abundant than carbon 14. But again, exists. So the way that we write isotopes is, this here is the new mass number, or the mass number associated with this carbon atom. So this carbon atom weighs 12, this carbon atom weighs 13. So this here's the mass number. Okay, so if we want to calculate the number of neutrons for carbon 12, so we just take that mass number, 12 minus the number of protons, which you told me was 6. So then I have 6 neutrons. So what about carbon 13? How many neutrons does carbon 13 have? So the new mass number is 13. So in this case, we'll take 13. Number of protons are never going to change. How many protons does carbon have again? 6. So the number of neutrons would be 7. Okay, so carbon 13 has 7 neutrons. So the difference between the mass of carbon 12 and the mass of carbon 13 is the number of neutrons. Does that make sense?
What does the number 12.011 mean?
So 12.011 is the atomic mass that's on the periodic table. And so when we look at the periodic table is all of these isotopes added together, right? So if it's 12.11, so that means that the majority of it is going to be carbon 12. We're going to have less than 1% that are less than 0.1% that's going to be carbon 13. So it'll be like 0.8 or 9, and then percent. And then this guy is going to be like 0.02%. Okay, really, really small. But if we took the averages of all of these guys, they would add up to that value, which is what is on the periodic table. Okay, but in reality, we're saying that the majority of carbon is carbon 12, but we have a little bit that's carbon 13 and very little that's carbon 14. Does that make sense?
Yes, thank you.
So here's the equation for the mass number. A represents the mass number, Z represents the number of protons or the atomic number, and N represents the number of neutrons. So we use this equation to calculate the number of neutrons. So when we're talking about isotopes, the only thing that's different between isotopes of carbon, protons are going to be exactly the same. The only thing that's different between carbon 12 carbon 13 and carbon 14 is the number of neutrons. Carbon 14 has how many neutrons? That's right, 8. So we have 14 minus 6, which is going to equal to 8 neutrons. Okay. Okay, so these again are called isotopes. Now, there's a couple of ways of writing isotopes. One is the way I wrote it up here. Another way is to write it like this. Let me clear my screen. Let's see, there we go. Okay. So here, we can write it like this. So carbon 12, and then here would be the atomic number. So up top is the mass number, at the bottom is the atomic number. So that's one way of writing it as well. You'll see it written both ways on your exams, and then also on in the literature as well. Another way of writing it is writing out the element, so carbon-12. So that means that this is isotope 12. This guy is isotope 13. Okay. Okay, so what I'd like you guys to do, can you guys write on my screen? Yes, no, maybe. I would like you guys to go ahead and fill this out. I'm going to give you guys, we'll say 10 minutes to fill out this table, knowing what you guys know. And pay attention. Now, this here is telling me that I have an isotope. And so this guy is going to be different than what we see on our periodic table. And our atomic mass, or our mass number, is going to be the number that's provided by here. It's not going to be the one that's provided by the periodic table. Does that make sense? Okay, you guys, you want to do it together? I don't see any writing on my board. I'm feeling lonely. Okay, let's go. So, what is the element symbol for barium?
Capital B-A.
Capital B, lowercase a.
Yeah.
Can you guys see that? Or should I choose a different color? That's better. Okay, what is the atomic number for barium?
Is it 56?
56. How many protons does barium have? "56", that's correct. How many neutrons does barium have? Or in this case, this isotope of barium. So this is the new mass number. So how many neutrons would that be? So that's the new mass number. 82. That is correct. Because then we just subtract 56 from 138, and that'll give me 82. Okay. Okay, so then how would we write the name of the isotope? In the same format as this guy. Anyone? So in this case, it would be barium. And then we put the new mass number, which is 138. Okay. Okay, so here we have oxygen. What is the symbol for oxygen?
Capital O.
Capital O. Okay, the atomic number for oxygen.
Eight.
That's right, 8. Number of protons for oxygen.
8.
Okay, so if I have 8 protons and I have 10 neutrons, what would be the new mass number? Because we know that
18.
mass number is going to be the sum of the number of protons plus the number of neutrons.
18.
18. Okay, so then what would be the nuclear symbol for this isotope of oxygen? What's going to be the superscript number? Superscript is the one on top.
18 divided by 8.
So it'll be 18 on top. And then on the bottom, we should have 8. Okay. And then we call this guy oxygen. What?
Eighteen.
Oxygen 18. My age. Okay. The next one. So it has an atomic number of 82. What has an atomic number of 82?
Lead.
Lead. The symbol for lead?
Capital B, lowercase b.
Capital P, lowercase b. Okay. Number of protons.
$82.
82. Number of neutrons. So we have the new mass number here.
124.
Yep, that's right. It's 124. And the nuclear symbol? So what's going on as the superscript?
124.
Are you sure?
Oh wait, no, 206.
206. And then what's going to be the subscript?
Is it 82?
82. And we're going to call this guy lead. Dash 206. Okay. And then the last one, the element that we're going to be talking about. This is our hint. What is it? That's right, zinc. the symbol for zinc? CN. The atomic number for zinc?
30.
Okay. Number of protons for zinc?
30.
Number of neutrons for zinc, in this case? Right, 36. The mass number for zinc? Okay, 66. And the nuclear symbol? Superscript is going to be, that's right, 66. And the subscript is going to be the atomic number, which is 30. That's right. Okay, questions, concerns? Cash, Kool-Aid? Okay. So this is the table filled out. Okay, now knowing what you guys know at this point, so which were disproved by what we found out about the atom on Dalton's atomic theory? Can it be something smaller than the atom itself? Or can it be broken down to smaller components, the atom? The answer is yes, because we have protons, neutrons, and electrons, okay? So these are the things that we figured out. So the atom is divisible because there's the existence of the protons, the neutrons, and the electrons. And then all atoms being identical, we know that that isn't true because we have isotopes. So isotopes are atoms that have the same element, but different masses. Okay, so that brings us to our next topic, the atomic mass. We've already talked about the atomic mass. So the atomic mass is basically based upon carbon. They use carbon-12 because carbon-12 is one of the most abundant isotopes that exist. And it works out, so they said that 1 unit is going to be equal to 1/12 of the mass of one carbon-12 atom. So that's going to be the premise of everything that's on our periodic table. It's based upon that, the carbon-12 isotope. So the mass, the atomic mass, so the average mass of an atom of an element compared to the atomic mass of the atom of a carbon is exactly 12 atomic mass units. So in other words, carbon weighs 12 atomic mass units. Okay. So the way that isotopes, the way that our atomic mass on a periodic table is provided, it's based upon the isotope and the abundance of the isotope. Here, this is basically using a mass spectrometer to separate the mass of neon. So these are the 3 isotopes of neon. We have neon 20. We have neon 21. And we have neon 22. Oops, screwed that one up. Okay, so if we take a look at this, this is the relative abundance of each of the different neon ions. Okay, so neon 20 is greater than, we'll say it's probably like 90, I'm going to say about 92%. Neon 21, I'm going to say that one is about, I'm going to say it's probably like 2%. And then neon 22, I'm going to say that guy is probably about 8%. Okay, so the way that our atomic mass is calculated is by taking the average of all of the isotopes together. The way that we do this is we take that percentage, we change it to decimals. So we get that 90% divided by 100 to change it to a decimal. And we multiply it by our 20. So in other words, we'd have 20 times 0.92 plus 2%, which is 21 times that 2%, which is 0.0 in a decimal form, 2 plus 22.0.00, oops. I got carried away with the zeros, 0.08. Now, these are rough estimates, so my numbers may be a little off, but it kind of gives you the idea.
So the equation you just wrote would equal the 92.
No, this whole equation is not going to equal the 92. It's going to equal the mass, approximately the atomic mass of neon as a whole. So it's going to be atomic mass of neon. Okay, so I get 20.58. So if you look on your periodic table, I'm a little off. Oh, sorry, that should be 6, not 8, since I can't do math. It should add to 100. So Okay, so I get 20.14 when I redo the math, because it should add up to a total of 100%. So 0.92, 0.2, and 0.06, that should add up to 100. So, or 1.0. Okay. So if we look at our periodic table, we get 20.18. So I'm a little off, but again, these are rough estimates. They're not going to give me the exact estimates. It gives us an idea. So because neon is 20.18 on the periodic table. And so if we add the exact numbers, we would get that mass exactly. Okay, so let's give this a shot on your end. Maybe. Okay. The natural distribution of isotopes of boron is 19.9% of boron 10 at a mass of 10.129370 units and 80.1% of boron 11 at 11.009355 units. Calculate the atomic mass of boron. So if we do this, we're going to change that percentage into a decimal form, and then we're going to multiply it by the mass that's given. Okay, so to do that, oops, sorry. So we have 0.199 times 10.012930 plus 0.801 times 11.00930055. So if we do that math, we have 3 sig figs here. We have 2, 4, 6, 8, 9 sig figs here. We have 3 sig figs here. And we have 2, 4, 6, 8, 9 sig figs here. So how many sig figs are we going to get by the multiplication? Three sig figs multiplied by 9 sig figs. How many sig figs should I end up with?
27.
I should end up with 27 sig figs. What is the rule about significant figures? Anybody remember? It's always the lowest number, right? So if we're doing multiplication, we have 3 sig figs here multiplied by 9 sig figs. So then we should end up with a total of 3 sig figs. Okay, so my answer should be 3 sig figs. So this guy would be 1.99 plus, that would be multiplying this by this. Then we have plus, again, 3 sig figs multiplied by 9 sig figs. So I get for 3 sig figs, it should be 8.82. And And then we add these together. Get 10.81. So if you look on your periodic table, what is the atomic mass for boron? Anyone? That's right. Okay. So remember, when we're doing multiplication, the number of sig figs, our answer should be for that multiplication product. That product should be the lowest number of sig figs. So this guy has 1, 2, 3 sig figs. This guy has 9 sig figs. So our answer should be 3 sig figs, which is 1.99. Same thing over here, 3 sig figs, 9 sig figs. Multiply by each other, our answer should be 3 sig figs. So you want to remember our significant figures, okay? Okay, so the next part, it says naturally occurring lithium is composed of 2 isotopes, 7.59% of 6.01512224 and 92.41% of 7.0160041 units. Determine the mass, the atomic mass of lithium. So we're going to do this exactly the same way. We're going to change our percentage into decimals. 0.7, oops, sorry, 0.0759 times 6.015124 plus 0.9241 times 7.0160041. That's going to equal. So how many sig figs do we have here? For this first number, the 0.0759. That's right, 3 sig figs. So we know that 3 sig figs is much lower to whatever this number is because there's like 2, 4, 6, 8. Okay, so 3 figs is smaller. So let's do the multiplication. 0.0759 times 6.015124. So this guy is 0.457 plus, how many sig figs do we have here? 4, that's right. So we need 4 sig figs for our answer. Value is 6.483, and then we add these together. Okay, so I get 6.94 for my lithium. What do you guys see on your periodic table?
.94 as well.
Okay, piece of cake. So usually the people that typically miss this problem typically miss it partially because they'll get some point sticking off because of the sig figs. Okay. So let me clear. Okay, so this is just basically showing you the percentage of abundance of some of the natural occurring isotopes. So here we have the hydrogen isotope. So we have, this guy is called, so this guy's called deuterium. This guy's called hydronium. So we have hydronium and our deuterium isotopes. I'm sorry, not sorry. It's protium. So the first one's called protium. This guy's called deuterium. So these are the helium isotopes. So beryllium, all of it is one isotope. So we can sit there and use these calculations, these values to sit there and calculate the atomic mass of the element on the periodic table, right? So for instance, we could do it for sulfur, right? By using these values and the percentages that they have. So these are the actual mass of the isotopes, right? It's not the rounded mass. So when we look at the mass number, it's that rounded mass. And if you take a look at it, it's pretty damn close to what you guys see here, right? So this guy, we'd round this guy up to 36 to get our 36 here. This guy would be 34. This guy would be 33. This guy would be 32. So it gives you pretty much that value, that rounded value. So this is the actual using the mass of the proton and the mass of the neutrons rather than the estimate that both of them equal about 1. Does that make sense? I know I'm talking really fast. You guys need some time to digest? Chomp on it? Or do you guys got it? Okay, good. Okay, so if on the exam, I give you calculate the atomic mass of sulfur using the data from the table 5.2. So if I give you table 5.2, I want you to do the calculations for sulfur. You guys will be able to do that, no problem?
I'm not sure.
You're not sure? Okay, so let's go over it. So let's get the information from table 5.2. Let's go back. So I'm just going to type down these values right on top of them. All right, below them. Oops. So Brittany, the exam is going to actually open up Friday morning, and it'll be open till Monday night. So we're going to start off with the one that we have the most abundant of, which is 94. So we're going to use 0.9493 times this value, 31.972070 0.69. This guy is going to be 0.0076 times 32.97145850. This guy's going to be 0.0429 times 33.96786683. And then the last one is going to be 0.0002 times 35.96708088. Okay. And so we got the data. So let's go and do those calculations. Start off with the first one. So how many sig figs do we have?
Is it 4?
Right, 4. So let's do that math. Okay, this guy, we have 4 sig figs. It's going to be 30.35. Okay, so our next one. So how many sig figs should I have here?
3?
Are you sure? Because remember, these guys are space holders.
Oh, so just 2 then?
That's right, 2. This guy is going to be 0. Point 25. Then we have this one here. So how many sig figs here?
Three?
3, that's right. Then we have the last one. How many sig figs here?
Is it just one?
That's right, just one. Zero point zero zero 7. Okay, so if I add these all together, okay, so we have 7 here. We draw our lines of significance. Let's see, that's 6. Carry the 1. That's 5. So that's 10. So that's 0. Point. 1. So then that's 32. So okay, so this would be our line of significance. So we use this guy to round up or round down. So we end up with 32.07. That's my answer, which is pretty close to what we got on the periodic table, which is 32.06. Okay. You see how that works?
Yes.
Okay, good. Okay. Okay, so let me clear the screen. So let's talk to you guys about the periodic table. We've kind of seen the periodic table. We've played with the periodic table and everything like that. So initially, the periodic table was arranged, and it was arranged by atomic mass initially. And there were huge errors with the atomic mass. And so then they later rearranged the periodic table based upon the atomic number, right, which is the number of protons. And so that's what it's currently arranged as now. So if we take a look, this is the periodic table, and you'll notice it's arranged in terms of the atomic number. And you notice that they have hydrogen listed twice. They're just showing you because hydrogen has some similarities to these, the alkali metals, and then it also has similarities to the halogens as well. So they had it shown in both cases. So in the old days, they used to have what we call the main group. So this A group, where it says A, so 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, right? So that was considered the main group. So before, we would kind of avoid these transitional metals and these metals down here because we didn't quite understand how to use them and the fact that they change. So then this guy would be the main group. This is what you basically learned most of your chemistry on because it all makes sense logically. And then, but over the years, we went back to naming this guy in terms of our groups. So up top, we have our groups. So that's group 1, group 2, group 3, group 4, group 5, group 6, group 7, group 8, group 9, group 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's the IUPAC nomenclature, and we call those guys groups. On the side, if you look on your periodic table that I gave you, you have what we call periods. And then, so that are going down. So this would be period 1, this would be period 2, this would be period 3, 4, 5, 6, 7. And you'll notice that these lanthanoids and actinoids, they actually fit into this spot right here. Okay, and I'll show you that on our periodic table. So let's see. Okay, so here's our periodic table. So these guys, these lactanoids and actinoids, they actually fit right in this spot. So reality, our periodic table looks like this. Let's see if I can make it smaller so you can see it. Okay, it's not letting me make it smaller. So, but you guys can see this here. These are your lactanoids, these are actinoids. This is where they actually sit. Okay, so that's the widened periodic table. The reason why we do it the way that we do it this way is because it's easier to fit on a piece of paper this way. Okay. Okay, we've already talked about the atomic number, we've talked about the chemical symbol, and we've talked about the mass number. You guys are already familiar with that. So I told you about the periods, I told you about the groups. So the thing about the groups, the elements that are in the same group, they're going to behave very similarly to each other. So they're going to have characteristics that are going to be very similar to each other. And so you want to keep that in mind. Okay. We've already talked about that main group, so that group A. So as I said, the main group isn't used on a lot of periodic tables anymore. We mainly use the IUPAC group numbers, and it makes it a little bit easier. But you'll still see it in some of the questions because some of the questions are kind of old, okay? So be familiar with it and what it means. So we have what we call transitional elements. We have metals, we have non-metals, and we have metalloids or transitional metals. Let me show you what those look like. Okay, so if we go up here, these guys are all transitional metals. These guys are called alkali metals. These guys are called alkaline metals. These are post-transitional metals. These guys are called metalloids. So metalloids have characteristics of metals and non-metals. These are all non-metals, so all of these guys are not metals. They don't behave as metals. Okay? Questions, concerns, Cash, Kool-Aid? So you guys can see how valuable P-table is. You can sit there and figure out what metals are. So these are all your metals right here. Okay? These guys are all of our metalloids. These are all of our non-metals. So okay. So our metals are going to be basically, you'll see that your transitional metals are from 3 to 12. So that's where your transitional metals sit. And then our metals are all over the place, right? And then we have like a step ladder on the end where the metals start impeding on the non-metals. And so that's also, you want to take consideration to that as well. Okay. So this is the atomic number, the chemical symbol, and the atomic mass of the third period element in group 6A or group 16. Okay, so let's look at our periodic table. Okay, it says we're looking at group 16. So here's group 16 right here. And then it's at the third period. This is the third period. So we go over to group 16, and that is what element? Okay, so period 3, group 16. So that element is sulfur. so that we put an S for sulfur. Its atomic number is 16. So Z equals 16. What was the other thing that they asked? And we know that this guy is a non-metal because it's green. Okay, you guys see how that works?
Yes.
Okay. Okay, so these are some of the common elements that you need to be familiar with. These are the ones that you're going to run across quite a bit. So you want to be familiar with those symbols, right? Your periodic table, all of this, everything in that chemical packet, that whole thing you guys can use on the exam. But the more you use it, the more it starts sticking up here. So you want to try to use it as much as possible when you're doing that work. So stuff will start sticking, okay? Okay, so this is just showing you some of the elements, those elements that were on that table. They're shown on this periodic table. So these are the ones that we want you guys to be familiar with. Okay, are there any questions? Good. Okay, since there are no questions, I'm going to let you guys go really early, and we'll pick up the next lecture, chapter 11. Will be the next topic that we'll be talking about. Okay. So I will see you guys on Friday.
What will we be doing for our lab this Friday?
What are we doing for the lab this Friday? I have to look. My lab order is all kind of screwed up. I have to get it rearranged.
Okay.
So you guys actually may be doing, because the topic that we're talking about, you may be doing a simulation for this one.
Okay.
So, okay.
Sounds good. Thank you.
Okay. Okay, I'll talk to you later.
Bye-bye.
Oh, I don't know if you have time for a
Yeah, I have
question.
time. Yep.
So for the lab number 3.
Yep.
I didn't record it, but did I have to send it to you? Like
You said
the
you didn't record it, you did not record it?
no, I didn't.
Okay. So the requirement is that you need to record yourself doing it. If not, record yourself, at least take pictures of yourself doing the lab. And then you need to give me the link to those pictures or put those pictures into the document in your lab report. And then also, or the link to the video that you take.
Oh, okay.
Okay, so, but get in the habit, so you're going to get deducted this time, and that's half your points.
All right, but we didn't have to send it, right? This
No,
time?
no, for this time, you have to give me the link to you doing it, right? Every time you're going to have to give me the link. I don't want to see the video. I mean, I'm going to see the video, but I want you guys to send me the link to the video. I don't want you to upload the video. Does that make sense?
Yeah.
Okay. So, because I need verification that you're doing the lab and not your little brother, or you're not doing it at all. You're just talking to, Maria. And so it's a way of verifying. So normally, if we're in class, I get to watch you do it, right? Or if you come to class, I watched you do it. Did you do it the day that we did it together?
No.
Yeah. So if you had done it the day that you did it together, you can use that video, because that video is being recorded, to sit there and use it, say, hey, I did the lab. I just did it via Zoom. So then it's being recorded already. So that's one of the benefits of doing it that day that we do it.
Do you have a recording like on the Canvas?
Yeah.
Or-
So Canvas has the ability to record. It's called Studio, and you're able to do it that way. Or you can use your cell phone, and then you just upload it to YouTube. Keep your YouTube and just give me the link. And by you giving me the link, I should have access to it.
Oh, okay.
Yeah, labs are Friday. Yes.
Okay, thank you.
Okay. Any other questions? Okay. Well, I will see you guys on Friday. You guys have a good day.
Bye. Thank you.
Bye.